Schneid guy.
So now we're going to talk about the ECG correlation to the cardiac action potentials and the important slopes that we've talked about in previous videos. First, let's take a look at this ECG tracing. I see the P wave here, which represents atrial muscle depolarization, the PR segment, and collectively the P wave and the PR segment is the PR interval. I have the QRS complex, the width being the QRS interval, and the ST segment leading into the T wave, and the beginning of the QRS complex all the way to the end of the T wave we call the QT interval. And then there's a TP segment until we get to the P wave again, and then we have the PR segment and QRS complex again. From one QRS complex to another, that's called the RR interval. So we have now our four important intervals: the PR interval, the QRS interval, the QT interval, and the RR interval. If we now look at the action potentials, we see we have an atrial action potential and a ventricular action potential. The reason why we're looking at these is that the ECG only records from the muscles. The nodal cells in the electrical system don't generate a strong enough electrical signal to be detected by the ECG. So I have my fast response action potentials shown for each of these locations, and to no surprise, phase 0 of all of these atrial muscle action potentials lines right up with the P wave. That's exactly what we'd expect because phase 0 is the depolarization phase. The reason why there's lots of action potentials here is that the P wave is representing all of those atrial muscle cells depolarizing. Now notice I have my phase 2, which nothing is happening electrically, it's stable, and that's lined right up with the stable portion of the PR segment. And then I have my repolarization phase, which is coinciding with the same time that the ventricles are depolarizing, and I don't see actually a waveform for the atrial repolarization, but that's in terms of time when it would be occurring. And then I have my phase 4, which is occurring throughout the rest. Now for the ventricle, I have phase 0 lining right up with the QRS complex, which again is what we'd expect because the ventricle depolarization is going to be recorded as the QRS complex. Now I have my phase 2 lined up with this ST segment, which is interesting now because I can see that during phase 4 of the atria, which is flat and stable, and the phase 2 of the ventricle, which is flat and stable, that is going to be when I have this flat segment. And then I have the repolarization phase in the ventricle action potential lining right up with the T wave. Then I have my phase 4, which is lined up with some of the phase 4 of the atria, and you can see that where they overlap is the TP segment here. You see right after the ventricular repolarization, and I'm in my phase 4, and I'm still in my phase 4 of the atria, that lines right up with this TP segment right here. And then if I want to go back to the PR segment for a second, I see that that lines up with the phase 2 of the atria as we discussed earlier, but also this latter part of phase 4. So whenever I have a stable flat segment, that lines up when the atria and ventricle are in their stable portions of their action potentials. Now where we put this all together is what are the important slopes and their effects on the ECG. And we can break this down with important slopes, the electrophysiological property that represents, the important channels that are involved, the important currents that are involved, clinically relevant locations that are going to be directly related to the ECG interval in question. So if we start with phase 4, remember that was the important determinant of firing rate because it affects automaticity. And the channels that are involved in phase 4 that are important for the SA node, which is a slow response fiber, are the HCN or funny channels and the L-type calcium channels. And here are the currents: HCN, an inward sodium current; L-type calcium channel, an inward calcium current. And that's why these are depolarizing currents. And in the SA node, the firing rate changes. That's going to change the RR interval. For example, if the firing rate, heart rate, goes up, I would expect the RR interval to go down. If the heart rate goes down, then I expect the RR interval to go up. They're inversely related. If I look at phase 0, that's conduction velocity. There's a couple of locations that are important. In the AV node, that's a slow response fiber. L-type calcium channels would be the important channel there because it's going to be affecting phase 0. In the ventricles, which are an example of a fast response action potential, it's voltage-gated sodium channels. So notice the difference. In the AV node, I'm thinking about inward calcium currents through the L-type calcium channel. And in the ventricles, I'm thinking of inward sodium current through the fast voltage-gated sodium channels. Now, the kinds of intervals that are going to be affected are going to be different here. When the AV node conduction is affected, the PR interval is going to be affected. And we can see that over here, that between the P wave and the QRS complex, there's this segment called the PR segment, and that's the time that is mostly taken up by the AV node conducting slowly. If AV conduction is slowed further and the delayed ventricular activation occurs, the PR segment will get longer and the PR interval will get longer. So these are going to be inversely related. If the AV conduction slows down, the PR interval goes up. If the AV conduction goes up, the PR interval goes down. And if I look at the ventricle conduction, phase 0 is lined right up with this QRS interval. That's going to be the direct effect of ventricular conduction. And if ventricular conduction is slowed, I see the QRS interval widen. We don't really see any situations where the ventricle conduction would be even faster than it is because it already is so fast. So we only really see slowing of ventricular conduction being an important consideration for the QRS interval. Finally, phase 3 is important in the ventricle. And in the ventricle, the APD is what the phase 3 is going to affect because the action potential duration is the complete action potential. And if the repolarization is slowed, for example, the action potential duration is going to get longer. And the main channel that's involved there is the rapid delayed rectifier potassium channel. That's the one that we can call KR, and that is going to give rise to this outward potassium current. So if I blocked these channels and I slowed the rate of repolarization, what would happen is I would get a prolongation of the QT interval. The action potential duration would get longer, and so would the QT interval. If the repolarization was sped up and I got a shortening of the action potential duration, the QT interval would go down. So these are very important intervals that can change with interventions that affect these channels and slopes.